Over the last few classes, we've gone over how to find the rate law of a reaction from the method of initial rates type thing. All right, that's where you take, come on, pen, work. Where you take experimental data of one reaction, several different experiments. You divide them out so that you can figure out the orders of those reactions, and then from that you can find the rate constant, the overall order of reaction, all that stuff. Okay. What you are writing from method of initial rates is what is called the differential rate law. All right. So a differential rate law looks something like this. Or whatever, okay? I just A to the first, B to the second. That's a differential rate law. All right. An integrated rate law is, and the derivation of how they get to the integrated rate law from the differential rate law is in your textbook. I'm fairly positive. You don't need to know how they got there. Remember, so integrated integrals, that's calculus stuff. Calculus is not a prerequisite for this course. A lot of you are currently taking calculus. So while it's grounded in calculus, you don't need to know the calculus behind it. Does that make sense? Okay. So I'm actually going to erase that and I'm going to write something out. So on page 11 of your guided notes, there's a summary of all of the integrated rate laws. I'm going to write them down up here. I would not take your time writing them down because they're in your guided notes, which can be found online as well. And I'll also show you how some of them are on the formula sheet. Bless you. All right, so zero order, the integrated rate law looks like this. For first order, the integrated rate law looks like this. And for second order, the integrated rate law looks like this. Okay. All three of these equations are in y equals mx plus b format. Okay? What does this symbol mean? No, standard was like a degree sign up in the upper right. In like physics or in math, when you have that symbol, what does it mean? Initial. So these all mean the initial concentration of whatever substance you're looking at. What?
Original.
Yes. Oh, yes, original. All of these rate laws, these integrated rate laws, are going to be for reactions in which there's only one reactant. Okay. So these are all the integrated rate laws for these. For zero, first, and second, those are the ones that they have derived and we commonly use the integrated rate law for them because they're the ones that are most likely the rate law, or sorry, the order of reaction for single reactant reactions. Bless you. Okay. You could certainly get half order or third order, and you could go through that whole derivation if you understand the calculus behind it, but not what you need for this course. Okay, zero, first, and second. The half-life formulas, or the half-life equations, look like this. And zero is the one I can never remember. A initial over 2K. T1 half equals 693 over K. T1 half equals 1 over notice how for 0 and second order, in the half-life equation, we have the initial concentration of that substance. Okay? And it's not in the first order half-life. Okay, let me back up a little bit. Last year, or 2 years ago, when you took chemistry for the first time, you probably learned that half-life is the amount of time it takes for 1/2 of the substance to decay. Right? You've probably heard that definition before. That is only true for first order. Okay? For second and 0 order, the actual length of half-life changes depending upon how much you have remaining. So each time you go through a half-life for 0 or for second order, the length of time it takes for the next half-life is different than what it just took. First order, the length of half-life is going to be constant the entire time. Okay, and we'll talk more about this next class. So after the long weekend, we'll talk more about this. All right, but just keep in mind. So this first order half-life equation is the one that is the most commonly seen, because it's what you actually, it's how you could have figured out back in like first year chem. Okay. 0.693 comes from the derivation of, from the integrated rate law to figuring out the length of half-life, and that just comes from the natural log of 2. Okay. When you set the integrated rate law to solve for t for 1/2 of it decaying, you end up having to do the natural log of 2, which is where that comes from. Okay. So I'm going to highlight. Highlight. There are, yeah, there we go. Those 3 that I just highlighted are on the formula sheet. The other 3 are not. Okay? Now we're going to do some problems where we're just going to be manipulating these formulas. Okay, so let's look at number 5. So we're told the decomposition of H2O2 to H2O and O2 follows first order kinetics. And it gives us a rate constant of 0.0410 minutes to the -1 at a particular temperature. Okay, the temperature doesn't matter. It's not part of the integrated rate law formula. And I give you the overall equation. We're going to calculate the concentration of H2O2 after 10 minutes if the initial concentration is 0.200 molar. All right, so which integrated rate law am I going to use? The first one? The first order one, because it tells me right here that it follows first order kinetics. So we're going to use the integrated rate law for first order. Whenever you have a problem like this where it's like, hey, after a certain amount of time, how much do you have? That's always going to be integrated rate law. Okay, because in the integrated rate law, we're comparing basically the concentration to the time. Okay? So, since it's first order, we're going to use this formula. Instead of writing A, I'm going to write H2O2 because that is my substance. And now let's plug in the information we know. We don't know this concentration because that's what we're solving for. So that's going to stay as natural log of H2O2. What is my rate constant? .0410, and that's minutes to the -1. How much time has passed for this problem? 10 minutes. What if I gave you the length of time that has passed in something other than minutes? You need to convert it to minutes because you need it to match the units from the rate constant. And it's easier to convert the time to the proper unit than trying to convert the rate constant to the proper unit. No, sometimes you have to find out what that order is, which I'll explain that in a little bit. Yep, so sometimes you have to do other stuff to figure out what order it is and then do the math with it. But let's just do the math right now, okay? And then plus natural log of our initial concentration, which is 0.2. Okay? Now let's pretend that we had 3 sig figs with our time as well. Let's just do sig figs, or let's just say let's do sig figs based off of our concentration. Okay. So we're going to start solving. Let's solve everything on the right. So negative 0.410 times 10 plus natural log of 0.2. Oh, sorry, not 0.410, 0.0410. So you'll get the natural log of H2O2 equals what? Who's there? Negative what? Oh, you just did this part. Gotcha. No. I wanted to solve the entire right side with the plus natural log of 0.2. All right. So now how are we going to get rid of that natural log? E both sides. Remember, opposite function of natural log is e to the x. All right, so you're going to do e of both sides, and that will give me the concentration of H2O2 after 10 minutes. So I would have just kept whatever you had here in your calculator and then press, e to the answer. And you should get what? 0.133. And what's your unit? Molarity. So that is the concentration of H2O2 after 10 minutes. Okay? We could find the concentration of H2O2 after any amount of time, as long as we know the initial concentration and we know what order of reaction it is. So we know which formula to plug it into. Okay? Now the reason why the formula matters is because the order of reaction will tell you how quickly the substance will go away. The substance will react. Okay? How quickly this H2O2 will convert into or decompose into H2O and O2. Okay? Because it's not always at the same rate. It's not always at the same with the same formula. Okay? Now from this, we're number 6, we're going to figure out how long it would take for half of the H2O2 to decompose. So we could use the integrated rate law again. What was my initial concentration of H2O2? 0.200. So if half of it has decomposed, what would be my final concentration? 0.100, right? And then we could solve for temperature. Or not temperature, that's time. We could solve for time, right? But why do it that way when on your formula sheet or in your brains, there's already a formula that tells you how long it would take for half of it to go away? Or you can use the T1 half equals 0.693 over K. Either way would work. So in the heat of the moment, in the middle of the test, and you forget that this formula right here, this half-life formula, will tell you that. If you plug it in to the integrated rate law, provided you're doing everything the right way, you should get the same answer. Okay? So, remember, half-life for first order only is dependent on the rate constant. What was our rate constant? 0.0410 minutes to the -1. So you're going to do 0.693 over 0.0410. And what do we get? And what's our unit? Minutes. Because this is a measurement of time, so we have to have a unit with it. That's the units on the rate constant. And that's another way you can know that it's first order. Because remember, all I'll write this in this maroon color. Our units on K, our K units, it's 1 over your time unit times your amount unit to the overall order minus 1. Kind of says that right there. I just had to squish that in. Okay? So remember, you can work backwards from the units to figure out what the order was. You can work backwards from the units on the K value to figure out what order it was. Or when you're finding K, you can find the units of it from the overall order. You can go either way. You should make sure you can find it either direction. Okay? So since our K units only are inverse time, we don't have any concentration units in there, or amount unit in there, that means it's first order. Because when it's first order, what's 1 minus 1? 0. So your amount unit is going to be raised to the 0 power, which goes away, because that's 1. Okay? So by looking at the K units, you can figure out, oh, this is first order. So that's another way the problem can tell you what order it is without actually explicitly stating, this is first order. Okay? All right, we're going to skip over 7, 8, and 9 because that is just more manipulation of the different formulas. We will eventually come back and do them, but I want to get to figuring out what the order of reaction is from the time and concentration data. So let's go ahead and skip to number 10. And this is where you're definitely going to need a calculator that can do statistical analysis. So make sure you have one of the TI 80 whatever calculators, TI calculators. Order minus 1. Overall order minus 1. All right. So skip into number 10. All righty. I'm going to write some stuff down, and then I'm going to show you how to plug it in. I actually have a little calculator thing right here. Okay, I found it on the internet. Okay, I know it's like an old school calculator, but it has all the same functions that yours do. Okay, but first, let me write down some stuff. So here we have this reaction, and we're given the time and the concentration of the reactant. So as we increase time, the concentration of that reactant is going down because it's decomposing into our products. We're going to set up in the stats function of our calculator 4 lists. Let me write down what those lists are, and then I'll pull up the emulator and we'll plug them in. Okay, L1 is going to be your time. Okay, L2 is going to be your concentration. L3 will be the natural log of L2. And then L4 will be the inverse of L2. Okay. So here on my calculator, I'm going to walk you through how to plug all this stuff in. Okay. So everyone click on the stat function. Make sure your calculator's on. Click on the stat function of your calculator. Okay, and then press enter to edit it. If you have anything in your list right now, you need to clear that out. The easiest way to do that is to scroll up so that you're highlighting whatever list. Like, so for example, in here, say I have stuff entered in. I'm just entering in random stuff right now. You don't have to do this. But say I want to clear that out. Instead of actually going through and pressing clear for every single one, scroll up so that L1 is highlighted, press clear, enter. And it'll clear out that entire list. Don't press delete. That deletes the list. Clear clears the contents. Okay? All right. So make sure that, and do that for all your lists so that you have them all cleared out. All right. So now we're going to enter, what are we putting in for L1? Time. So let's just go ahead and enter in our time. So put in those time values. Do you mind answering that real quick? For who? Oh, okay. Whoa, isn't that fun? Okay. So you have your time data entered in? And now go over to L2 and enter in all your concentration data. E-3, 1.27, E-3, 1.18, E-3. Enter. All right, when you have L1 and L2 filled in, eyes up here. That way I know we're ready to move on. I like that I found this emulator because then you can see exactly what buttons I'm pressing. Even though I can't really press them, I have to tap them with the pen. Okay, anyway, so now we're going to put in, for L3, we're going to do natural log of L2. Now, basically, we need to have the natural log of every single one of these concentrations. You can make the calculator do the work for you. Instead of actually getting out of here and calculating each one and writing it down, tell the calculator to do Ln of L2. So instead of being here, you want to scroll up so that you're highlighting L3. Okay? And then you're going to type natural log, which is this button over here, Ln, of L2. To type in L2, you're going to do second and then the 2 button, because that's the second function of 2. And then press enter, and that does the natural log of every single thing that was here is right here. Mind blown, right? Okay? And then for L4, we're going to do 1 over L2. We're going to do that the same way. So we're going to scroll over so that L4, and scroll up to highlight L4, and then type 1 over L2. Enter. You guys are so funny. All right? So you should get really big values here, because you're doing 1 over a fairly small number, so they should be very big. Yeah? Do you have your lists populated? All right, we want to get out of here. How do you don't want to press clear, because that's going to clear this first data point. So instead, press second quit. And now what we want to do is, before we do the analysis, we want to make sure that our calculator is set with diagnostics on, okay? There's 2 ways to get to this. On this old calculator that I have up on the screen, it's not going to be the same way as most of yours, okay? But everyone press mode. And down near the bottom, you might have to scroll down, and it might have to go to the next page. Mine doesn't have another page, but somewhere on there, there'll be something that says Stat Diagnostics. Do you see that? Please make sure that the on is highlighted to turn Stat Diagnostics on. If you don't have that in the mode, get back out of there. And you can always turn on Stat Diagnostics from the catalog. So if you press second, 0, it opens up the entire catalog of all the different functions that the calculator can do. So if you can't remember what menu it's under, you can always go to the catalog. It's automatically, see this little A in the upper right-hand corner? It's telling you that alpha lock is on. So whatever you type, it'll be doing the green for this one. It'll be doing the alpha function of that. So we want to press the x to the -1, which is the alpha letter D. So that jumps down to all the programs and the functions that start with the letter D. And then we're going to scroll down to diagnostic on. And then press enter, enter. Done. It's turned diagnostics on. And you'll see why we need diagnostics on in just a little bit. Okay? So now, press stat again. And this time go over to calc. And we're going to run the linear regression of each thing. So we are going to run a linear regression. I'll bring the calculator back, don't worry. We're going to run it for L1 versus L2. We're going to run it for L1 versus L3. And we're going to run it for L1 versus L4. Okay? So, and for each of those, we're going to be writing down some information. We're going to write down the A and the R squared. All right? Now, back here. So we're going to go down to lin/reg. Make sure you're doing number 4 and not number whatever that one is. I think it's 8 for most of you guys. But make sure you're doing ax plus b, not a plus bx. Okay, so ax plus b. Enter. Now, most of you probably have more information showing than I do right now, because most of you have an updated calculator than my emulator. Okay, when you're doing that, you can tell it to set the x list to L1 and the y list to L2. Remember, second and then 2 sets it to be L2. If you have it like this, what you want to do is second L1, comma, second L2. I actually didn't need to do that for this first one because that's the default. Okay, L1, L2 will always be the default when you don't have that menu function. Well, you can be like, X list is this, Y list is this, and then enter. When it's this type, you have to, if it's not L1, L2, you have to tell it something else, okay? Then you're going to press enter. Most of you will have to press enter a couple times, okay? And then from that, we're given the A, B, R squared, and R. All we care about are the A and the R squared. Now, as soon as I start writing on the board, I'm going to lose my calculator, so I have it on my handheld calculator. But A is negative 4 times 10 to the negative 8, and R squared is 0.9944. I'm going to leave it there. Okay? And now, we're going to do the same thing for L1 and L3. So go back to stats, over to calc, down to lin/reg, and it'll respond when I press enter. And then now I wanted to do L1 versus L3. Enter. So my A is negative, oh, I forgot to change it on my handheld calculator. Negative 3.41 times 10 to the negative 5, and my R squared is 0.9998. Okay. And then last one is back to this, down to lin/reg, and this time we're going to do L1, comma L4, which is the 4 button. Okay. So now on this, we're going to have 0.0296 and 0.9942. All right. Questions on that? And don't worry, I'm recording this, so if you ever need to walk through again how to, clear a list or anything like that, you can always watch this video. Okay. So now, from this, what all this means. So we just did a whole bunch of stuff with the calculator, and you're like, what are we doing with all this? The whole point of this was to figure out which graph, which set of data gives me my straightest line. And that's why we wanted the R squared value. Okay? So which R squared value is closest to 1? L1, L3. Okay? When the natural log of concentration and time gives us the straightest line, that means it's first order. If it was concentration and time that gave me the straightest line, then it'd be 0 order. And if it was inverse concentration and time that gave me the straightest line, it'd be second order. Okay? I'll write out some stuff in just a little bit on that, but this means it's first order. Okay? So the way we're going to justify that is, like, for full credit, you need to say first order because the linear regression, you could say the lin-reg of time and natural log of concentration gave an R squared value closest to 1. Okay? So that answers the first question, determining the order of the reaction. Okay. Now our K value, the K is with units. K with units. The K value, now remember, let me back up just a little bit to here. Remember, our integrated rate law was always in y equals mx plus b. What does m refer to? The slope, which is a from our calculator, because it's ax plus b instead of mx plus b. I don't know why they can't be consistent. So a and m are the same thing. For the first order integrated rate law, m is negative k. Okay? So what's our a? That's negative k. So what's k? Yeah, just the positive slope. So 3.41 times 10 to the negative fifth. And our units, we can easily figure out the units because what order is this? First order, and units for first order reactions are always just 1 over the time unit. And what's our time unit? Seconds. So you can write seconds to the negative 1, or you can do 1 over seconds. I don't care. Okay? So that's our K value. Now we're going to write the rate laws. Oh, I don't want to do pink because I already did that. I will do green. We're going to write the rate laws. Remember, we have two different types of rate laws. We have differential and integrated. So our differential rate law, that's going to be rate equals K times the concentration. What's our reactant? N2O5. What's going to be the order of reaction? Or its exponent? 1, because we figured out it was first order. So that's our differential rate law. Our integrated rate law, you would just, look at the formula sheet or remember that, hey, that's natural log N2O5 equals negative KT plus natural log N2O5 initial. Okay. When you're writing the rate laws, you don't need to put the values for K in there because it just makes it messy. Right? Normally we write the rate law and then we identify what K is. Right? Now say this were a problem where, hey, I gave you this information, this time and concentration data, and I said, hey, figure out the order of reaction. And then once you figure out the order of reaction by doing the linear regression analysis, then I asked you questions of like plugging and chugging your formula, like what we did in number 5 and 6. Okay, that's where you would need to, how you figure out the rate law, how you figure out the order prior to doing the math with it. Now what if this were a test question like that, but you somehow messed up in your statistical analysis and you found that it was second order, and then you gave the rate constant for second order with proper units as if it were second order, and then you gave me rate laws for second order, and then you did all the math with the wrong rate law. Where would you lose points? Only in the first part. Exactly. Because remember, it's process oriented. If you make a silly mistake early on, but then you do everything right from that wrong identification of the rate of the order, you'll get the points everywhere else. So keep that in mind if in the heat of the moment you can't remember how to find the order of reaction from time and concentration data. Pick 0 first or second and do the math correctly from that rate law. Don't pick third because we don't have an integrated rate law for that. And I'm not going to ask you to derive that. Okay? Questions? All right, before we move on, I do want to I want to insert a page after current. Okay, so like I said, the whole point of that was to figure out which one's going to give us the straightest line. So just a reminder, so zero order, when we run, time is always going to be our y-axis. Sorry, no, that's an x-axis. Time is always going to be our x-axis. And for zero order, concentration is our y. What slope does that have? Has a negative slope based off of this. See, negative slope. 0 and first are both negative. Second is positive. That's supposed to be a straight line. Okay. First order, that's going to be the natural log of concentration versus time, and that would also be a negative slope with a straight line. Second order is inverse or reciprocal concentration versus time, and that's a positive slope. So if we were to have a set of data for a reaction that is second order, but we graphed it as if it were first order, we did natural log versus time, we would still get a negative slope, but it would be curved. It wouldn't be a straight line. So that's how you know, hey, it's probably not first order. But if we graph inverse or reciprocal concentration versus time, we get a straight line. Oh, it's second order. Okay? So concentration, natural log, reciprocal. And I'm making a point to write reciprocal and not inverse because then it's in alphabetical order. To help you remember, 0, 1, 2, concentration, natural log, reciprocal. To help you remember the order that they should go in. Okay? All right, I'm going to pause the video here while you guys work on the next problem. Okay? So this one, it's a little bit more data to put in, but start going through the motions, figuring out, like, you're not going to do any math with it, but you have to basically do what we just did with the last problem. So I'm going to pause it here while you guys work on that. All right, so now that you've had a chance to do this one, I'm not going to go through the whole showing you how to plug it into the calculator, but what order did you guys figure out that this was? You should have figured out that it was second order. And remember, just saying second order is not enough. Like if this were an actual test question, it would say like, what order of reaction is it? And justify your answer. So what do we need to say in addition to just second order? So because ln reg of time versus 1 over concentration, that's a weird bracket. Okay, cool. So something along those lines. Basically that, you know, this, or you could say the slope was the straightest, it gave the straightest line, whatever. Because that's really what r squared means. Okay? All right. So from this, what is our k value? Yeah. So for second order, the integrated rate law, it's positive kt. So it's just slope is k for that one. K will never be negative. It can only be positive. Okay? Because it's telling you kind of like proportionally how it's changing the reaction. Or the rate. What are our units for second order? Times molarity to the negative 1 as well. Because remember, it's 1 over the time unit times the concentration unit to the overall order minus 1. Since we're second order, what's 2 minus 1? 1, so we have to have concentration in there as well. And both of those are on the bottom, or you could say it's seconds to the negative 1, molarity to the negative 1. All right, what is our differential rate law? Rate equals And then our integrated rate law looks like what? Okay, and then if we had actual math problems from that, we would use the integrated rate law. Okay? So that's it of integrated rate law. I'm going to stop this video, and then I'm going to start recording again for mechanisms.